So, hello everyone. My name is Marie Tahon. So I am leading the team about explainability for diarization. So this is quite a huge team, as Sanjeev has presented. We are at least 31 participants from 9 countries. So we had to manage everything during these 6 weeks. And our topic focus on diarization. So what is the state of the art for now in this field? So we know how to process multi-speaker speech signals. For example, those who are coming from archivists, broadcast news, and so on. We know that we have some tools to make some speech segmentation to detect where there is noise, the silence, or when there is speech. We know how to make some speaker diarization to find some mono-speaker speech segments. And we also know how to make some speech transcription on these mono-speaker segments. So what are we going to do in this experiment, in this workshop? So we are going to address some very specific question regarding explainability. So I'm going to go deeper in the definition of this word. For example, here you have a speech signal, and we have retrieved 3 speakers with our diarization system. And we have two speakers, the blue and the yellow one. The system detected that they are different, so we can wonder why they are different. Is it reasonable to have different clusters for these 2 speakers? And probably our system can help us to investigate this question. And we can have some answers. For example, on the left, it is a male. On the right, it is a female. And we also know that the pitch, the fundamental frequency, will explain 70% of the decision. We can also wonder why there is a boundary. So here, at the beginning of the yellow speaker term. So this boundary is a bit problematic because so there is no time-aligned transcription, but you can see that the boundary fit in the middle of a word. So why the system, the diarization system, find a boundary just at this time? We can investigate a bit that and provide some new information. For example, on the left we have no music, and on the right we have music, so that can explain why the system finds the boundary here. But we also know that there is a break in the linguistic cohesion before the word déjà. So maybe we can wonder if this decision is correct or not, and we have to let the decision to the human. Another example, we found here a very short segment for the blue speaker, and this very short segment have a very low confidence from our system. So we can wonder if this segment needs to be clustered with the blue one, or if it is not reasonable to do so. So we investigate a bit this, and we found that the emotional state is very high. We have a high activation for this speaker. So we also know that the loudness explains 64% of the decision. So loudness is related to energy, and we know that activation is quite correlated with loudness. So maybe this can explain why, in fact, it is really the same speaker as the blue one, but just it's a different speaker. It's a different way of speaking because he has a high activation. So to answer all the green answer, we are going to provide some different tools and systems in order to investigate and to give some insights of this question. So to better define what our formal word of explainability, so we decided to split the word in 3 parts. The first part is the real word, so what we can hear as a human. We know that the human perception can discriminate some segments, so we can say before there is music and before there is no music and after there is music. We can also, as a human, say, okay, there is an error because it's an anomalous detection. There is something strong erroneous here. So this is our real world. When we build an automatic system, such as, for example, speaker verification or diarization system, we are going to have a representation. So this representation is usually uninterpretable. We cannot investigate what is inside, but it is really relevant for the system to give good performances. So we would like to investigate a little bit what is inside this representation world. And we can explain this representation by constraining this latent space. We can also explain it by adding some probes, some gender or emotion classifier on top of it. And we can also have some perturbation mechanisms, so we can modify the input signal and see how it can change the representation and how it can change the results, the performances. But we want to go further, so we are going to add another word, so the informative word. In this word, we have put a lot of things, but even a lot is not enough. So in this word, we have descriptive variables, such as phonetic information, so we have phonetic alignment, word alignment, transcription. We can also have topics. We can also have gender, emotion, and we also retrieve some acoustic descriptors. So in this presentation, we are mainly focusing on some specific acoustic descriptors that are extracted with OpenSmile. And these descriptors are supposed to represent the prosody, so mainly intonation, energy, rhythm, and spectral content. So this informative world is really important because we have experts that can interpret this kind of thing. We know, for example, that F0 is related to gender. We know that prosody is related to emotion. But the question is that we don't know how this word is related to the representation world. So in this workshop, we have tried to investigate how we can define this linking function between the representation and the interpretation in the informative world. So this is pending an open question because we didn't solve any, the problem, of course, but we are going into this direction. So regarding the organization, we have mainly three different parts. The first part is almost technical, so we would like to provide a good system that provides the speaker when he speaks and how he speaks. So we want to provide a multitask, multimodal speaker diarization output. So here multimodal means that we are taking into account acoustic and linguistic information. And to do so, we propose a different system, a speech segmentation system that can output music, speech, noise, and overlap at the same time. A speaker segmentation and clustering, so diarization system. And also, we wanted at the beginning to have topic information with respect to time, but in fact, it's really difficult, so we didn't get into this thing. And also, we would like to better characterize the speaker. For example, the yellow one is unknown, so we would like to characterize him. So we would like to provide some attributes, for example, linguistic information, named entities, area of expertise. We can also retrieve the gender, emotion, role, overlap, etc. And we are going to include also model confidence for all of that. And finally, we are going to this explainability and interpretability question. So, for example, there is a speaker that says, in this recording, a few years ago, you said it was me, so maybe onlat, but in fact, it's not me. So can you prove that it is really me? So we have to explain the decision of the model. So we have to explain that the blue speaker is really onlat and why. So why there is the boundary, so why we decided to cut this segment, why this audio segment belongs to this speaker, the blue one, why this audio segment has been clustered with this other one, so with the other blue ones, and what are the attributes that characterize this speaker. So mainly our system will take into in input a speech signal and also the transcription. So we can have the reference transcription, but we can also retrieve it from an automatic speech recognition system. And the global system will return the speech segmentation, but enriched with overlap information, music, and noise. At the same time, the diarization, speaker diarization, a list of attributes and model confidence, and also the explanations. We also wanted during this workshop to provide an evaluation protocol, so we are going to set up some ideas, and we plan to run this protocol after the workshop. So the main scheme of the presentation will be divided according this global scheme. So we have this entry in speech. We have acoustic embedding, so we are going to investigate this representation space. So we can segmentate the speech and then give the outputs to the diarization system. From this diarization system, we have mono-speaker segments, so we can get the gender and emotion. We also can run some speaker verification, and we can extract named entities and topics from the linguistic information. So there are two things that I will not talk about because we didn't investigate it in details. The speaker verification system, so we have used on-the-shelf system, so we're not going to detail it. We are using a standard X-vector system. And topic modeling, so also we have done some work on that, but for analysis, not to develop new systems. And regarding explainability, so if we integrate these explainable things, we have here interpretable speaker embeddings, and we will provide explanation for all the output of the system. Okay, so I will start with the data we have prepared for the workshop. Just regarding the general organization, from time to time you will see a yellow stripe, a yellow flag, and this is the time for short questions, so we can take some questions at that moment. So regarding data, of course, we would like to retrieve a lot of information, and at the same time, we would like to train a single model, but on top of different annotations. So the first issue we have is that there is no heterogeneity of the annotation across the different databases. So how you can see in this table, you have the database on the left, and there is no yes in all the columns. So it's very difficult to unify this. So we had to manage this kind of thing. For the evaluation data, so we have evaluated our system on broadcast data, mainly Spanish and French data, also diarized for diarization. So there we face some challenges. We have long files. We have variable speaker turn durations from very short to very long segments. We have variable number of speakers. So in Allies, for example, we have up to 74 speakers in the same file, and in average 11 speakers. And we also have spontaneous speech. So we have made a huge work for preparing the data. So we have a clean evaluation test set that has been provided by Elia Data mainly. So we have only 35 files for the evaluation, but in terms of duration, it means 10 hours. We have annotation in segmentation and speaker turns plus overlap, and the manual transcription. We have also prepared the force alignment of the phonemes and the words, so automatic force alignment, in order to investigate the phonetic information. So now I will let the floor for low resource data.
Thank you, Marie. I'm Sarah. So probably this is the first time we look into this data. So this data was collected in Borneo Island. Hopefully you know where is that. I have placed the Google map there. Very nice. It's quite big island. So this is Sarawak Malay. It's commonly spoken in the island itself, mostly in the northwest of the Borneo part. So we've collected, this is one of the languages that we have collected using our web platform. We have many more. So this is the first time we are going to embark our journey on speech recognition, speaker diarization for this particular language. But the results will not be presented by me, it will be presented by Zul later on. So it's a conversation data. As of now, we have transcribed the data and also labeled it for speaker diarization tasks. So for the transcribed data, we have about 1 hour and 26 minutes, 52 speakers. We have those details over there. And we have unlabeled data, which is about 12 hours. of the same language. So we're going to see whether with this under-resourced language, we will do some discovery or not on speaker diarization. We have already released the transcribed data on GitHub. I forgot to put that link there. So some of the challenges that we have in this data set is that it has been collected in various environments within the 2018 to 2022. Due to COVID, because we work with students due to low resource funds. We work with students, so they were at home and then they were collecting the data using their phones. And so we have this kind of challenges. So you will probably listen, there are some background noise. We have music, cars, bikes, maybe some chickens, and also dogs behind. So those are the kind of challenges that we see in this kind of data set. But it's okay, we are thankful for the workshop and we learn a lot along the way. So stay tuned for the first investigation on our speaker diarization strategy for low resource language. And hold on tight, you will start to see our diarization team to do their presentation. So I pass to Martin.
Thank you. So I'm Martin, and I represent the work we did on multi-segmentation, multitask segmentation. So as Marie said, the goal we have is to segment an GNU signal into 4 classes: speech, music, noise, and overlap. And maybe more if it's relevant. So what we came from, we have 2 separate baselines. One that can do overlap speech detection and speech segmentation at the same time, and one that can separate speech, music, and noise. So now we want to fuse them. To do this, we are using the multi-label paradigm, like we can output multiple labels at the same time. So the main challenge is for our work is the data. We have a lot of classes and no data sets with every one of these classes at the same time. So to do this, we are using a method to fuse the partially annotated data. We are masking classes in the data sets that are not present to use it in the same loss. So it's only possible because we're using the multi-label approach. And so this method is now implemented into Pioneer. So after the workshop. We tried different approach, different features. First, the traditional set of features, MFCCs and chromas, and the derivative. We compared them to leaf, learnable filter banks leaf that is a derivative of SyncNet that is supposed to be better for music. And finally, we tried the pre-trained self-supervised model. So in our case, WaveLM with the base plus and the large model. And we tried different type of models. So our main element was the TCN, the temporal convolution network. That's causal 1D convolution. And we tried 2 other approach. First, anomaly fusion, so taking multiple features, fusing them, and then going through TCN, or using different branches, different TCN for each features, and choose them at the end. So, on the results we got with the base TCN for different features, we can see that the WaveLM by large is over other features, clearly. And it's even at the same point as the separate baseline we get. So we basically succeed into making a single system that is as efficient as the separated one. And if we compare the alternative, the fusion that we tried, the single branch system is still better than the other. So now we have a system that works, and we might not want to know why. So to do this, we tried to clusterize WaveLM features using a k-mean, and the idea was to project WaveLM into a more interpretable space, like a smaller space that we could evaluate after. And we are training a classification system, a segmentation system, using the clusters as features. So we have 2 types of features. Either we take only the index of the cluster, or the distance to every cluster. So I will only speak about the index one. It's not the best performing, but it's the more interesting. Because as you can see, the results are not that bad. Clearly, for the developed part, it don't even degrade, but we only have one features compared to the 1024 from WaveLM at the start. So we wondered why. So maybe it's the representation of cluster that is really good. Clearly not. We are looking at the purity on this graph, and the cluster are all mixed. We can't see anything on this side, but if we try the second experiment by shuffling the WaveLM frame after the extraction, and try to see the importance of the temporal information in WaveLM and for the classes. And as you can see, for the music, the speech, the music, and the noise, it don't degrade as much. It don't degrade a lot. But for the overlap, the temporal information seems to be far more important than the dimension itself. So, as a quick conclusion, we presented the first segmentation model as able to provide annotation for speech overlap, music, and noise simultaneously, with competitive performances compared to single task systems, and using partially annotated datasets. We can say also that the overlap segmentation seems to rely more on temporal structure of features compared to the features themselves. And theoretically, our model can be expanded to more class.
Hello, I'm Alexis. So now we have this compound dataset, which is made of different sub-datasets, and each of them has a different subset of classes that are annotated. And what this means is that for some classes, like noise and music, we have lots of hours where music and noise might be present, but we don't have any annotation on them. Now, a way to deal with that is with semi-supervised learning. So this is the usual, like most classical setup, I think, where you have some annotated dataset, some unannotated dataset, which is usually bigger because it's easier to get data than to annotate it. And then when you sample from it, on the annotated dataset, you get both the input and the desired output. So in our case, the audio and the segmentation data. And for the unannotated dataset, you only have the audio. To deal with that, one way to do it is with teacher models. So in this case, you put your teacher model into some kind of pipeline, where in the end you obtain an output that you use as a pseudo label, which means that you can then use it in training as if it were the true label of the data. Now, in our case, the setup is a bit more convoluted because we have this compound dataset, and when we sample a batch, we have a mix of presence and absence of annotation. But the idea, I think, stays the same, and that doesn't meaningfully change how it works. Now, for the experiment we did, we focused on diehard and especially on the overlap class. So diehard is a speaker diarization dataset, which is made of 11 subdomains, and this means that it makes the dataset very practical, very easy to split. And what we did was split the domain in two parts, which is the annotated part and the unannotated part, so split A and split B. And we will pretend that this split B is our unannotated dataset. And so then, in the first phase, we can train a teacher model on the split A, which we consider as annotated. And on the second phase, we can try to train a student model on both split A and on split B, where we will be using pseudo labels, which are provided by this teacher model. And in this case, the validation and test of split B, we use the true labels because what we want to do is really see how the training goes. Now, how to select pseudo-labels, because we probably do not want to use all the pseudo-labels generated by the model, because some of them will be good, some of them will be bad. So if we look a bit closer to the output of our model, we have this segmentation output, and it's the end output, and this is what is desired for the user. But if we look before the binarization threshold, we have these row posteriors, which represent some kind of quote-unquote probability of the class. So if you get 0.8, you might expect that there is about an 80% chance that the class C is present, and then 20% chance that the class C is absent. Now, of course, there is no mathematical certainty behind that. Models do not have to follow this, but we will assume that these posteriors can be taken as some kind of proxy for this probability. And from this, we can also derive some notion of confidence. It's the same, it's a bit blurry what is confidence in this case, but we can assume that if the model outputs extreme results, like very close to 1 or very close to 0, it's probably more confident than if it outputs something that's more in the middle. Now, what kind of strategies can we use to select the pseudo-labels given this confidence? So to visualize that, let's have a batch that we have sorted from the least confident samples to the most confident samples. So sample data where the model is least confident, sample data where the model is most confident. The first strategy will be to first select samples where the model is the most confident. Second strategy is to first sample data where the model is the least confident. And third strategy is to sample data between two quantiles of confidence, so taking a slice of data. Now, a bit of a tangential question is, what if we could actually annotate some of the data in split B? So if we annotate 0% of the data, we just get our baseline, we haven't done anything. If we annotate all of it, this is probably our top line, because then it's just fully supervised learning. But then if we annotate some arbitrary percent between 0 and 100%, we have different strategies to do so. So first, our first strategy, which is to annotate using like providing the labels where the model is the most confident first, we get a fairly linear improvement in performance. If we use the strategy 3, we get fairly linear decrease in performance. And most importantly, if we use the strategy 2, so if we select the least confident data first to provide labels on it, we get a really big improvement in performance very quickly with a very low amount of data. So if here we provide only 10% of the data, but where the model is very confident, and we almost manage to reach the same performance as if we provided all of the data. Now, what happens if we actually try to do semi-supervised learning, so with pseudo-labels? This is the kind of thing we were expecting, where with the green curve, we have no improvement when we use 0% of the pseudo-labels. We probably don't have much of an improvement, or maybe it will degrade if we use all of the pseudo-labels, because then you use a mix of data that is correct and incorrect. And at some point in the middle, with some kind of strategy, we should have some peak. Now, our intuition was maybe a bit incorrect, because this is what we got. And the first thing you can see is this big dip in performance at the middle. And this is where the output of the model is neither really confident, neither really unconfident. And the best results are obtained on when selecting data where the model is between 30 and 40% of confidence. Now, these results are a bit strange, and I think that can be attributed to multiple factors. First, we are not using any augmentation, and I think that's actually a key part for semi-supervised learning, and we can't expect really a big and consistent improvement in performance without that. The second point is that our data comes from different distribution, because we are using diehard, and what we are trying to do is both semi-supervised learning and domain adaptation, so we are making the task even harder. And then we use uncalibrated posteriors. So because we have no guarantee about the calibration of our model, about what these posteriors are supposed to represent. We can't really use any fancy or reliable selection strategy, and we are mostly forced to use quantiles. But if we had calibrated posteriors, we could use probably better strategies. The second point is that where the model is very confident, it is actually good enough. What I mean by that is that if you provide annotation here, you will not increase the quality of the model. But these predictions are very variable because this means that the model is mostly right here, and they can then be used in augmentation schemes for semi-supervised learning. And finally, if we look at the data where the model is not very confident at all, this is where probably the decision boundary is not clear for the model. And if we provide samples of data here, we can probably help the model a lot to improve its performance.
Hi, my name is Jasmine. I will be talking about calibration in the context of Alexis' experiments. Well, we will say a probabilistic classifier is calibrated if it generates scores that match the frequency of the classes given those scores. We want these calibrated scores because we want them to be interpretable and because we want to take optimal based decisions. And we suppose this will be beneficial for the pseudo-labeling context. In our experiments, we work with post-hoc calibration in a post-hoc calibration fashion, where we take our raw scores, find a calibration transformation to obtain calibrated scores, and then compare the original and the calibrated scores. And we measure calibration in terms of expected calibration error, which is kind of like the new standard metric for calibration in the machine learning community, and a calibration loss, that is the difference between the log loss in the raw scores and in the calibrated scores. Our question is like, we want to analyze the performance of the model on seen and unseen domains. Alexis already explained the composition of diehard, so we will consider D1 and 2 D5 domains in diehard as seen. We will train the model and train the calibrator on those domains, and we will test on domains from D1 to D11. This means that we will be testing on seen and unseen domains. Concretely, our experiment on calibration will consist on taking Alexis' teacher model, training a linear logistic regression with the domains from D1 to D5 to obtain the calibration parameters with which we will transform our scores and calibrate the complete test set from domains D1 to 11 as kind of like as it comes. But when we diagnose the calibration of our model, this is a reliability diagram that shows in the x-axis the bin posteriors of the model, and on the y-axis the frequency of the positive class in each of the bins. We see that the model, because everything lies on the blue bars lie on the diagonal, we see that the model globally is kind of like perfectly calibrated, or more or less. And we also see that from expected calibration error and our calibration loss. So, but however, when we see like the calibration, when we start analyzing the calibration by domain and we do an analysis from D1 to D11, we see that calibration varies a lot within the domains. It has better performance, as we would expect, in the domains seen during training, and worse one in the domains not seen during training, and which makes us think that probably selecting only one threshold for the entire data won't be useful. The reliability diagram shows as an example, for example, domain D7, which is highly uncalibrated. And also another thing that we saw is that probably domain mismatch affects more calibration than classification from what we can see from the equal error rate values. But I chose equal error rate, but there was lots of other metrics. So this I will skip. And these are the conclusions for the whole group.
So for the multitask segmentation group, some takeaways. First, we are able to create a great model that can segment another signal into 4 classes simultaneously and output calibrated score. And we propose also a framework to use the partially annotated data. We raised, thanks to Rasmin and Alexis, the issue of global calibration against in-domain calibration. And we demonstrated the importance of temporal information in protein features. And for future works, we want to demonstrate that it's possible to extend our model to new classes and out-of-domain data with calibration. So if you have some questions, now is the time. So we can continue.
Okay. So, hello. My name is Anya, and as was said before, the diarization is actually the core component of the whole team. So here I'm going to introduce the work done by the diarization subteam of our team. And first, I would like to maybe remind you very shortly what the diarization is. So what do we expect from the diarization system is that for a given audio file, it's supposed to tell us how many speakers do appear in the file and when do they speak. And there are two general directions that people usually take when addressing this problem. Either this would be the clustering-based approaches, as for example our baselines are, which are agglomerative hierarchical clustering and VBX, but I'm not going to describe them since I already did it here once. And in this kind of approaches, you assume that, or the way you proceed is you split the given audio file into short overlapping segments, you extract some speaker embedding from each of the segments, and then you try to cluster the speaker embeddings. And for many clustering methods, it's relatively easy to track why you decided to cluster two embeddings together. So from explainability point of view, it's a nice feature of this model. However, the typical embeddings that we have here are not explainable, so this is a drawback of this approach, but if we manage to replace the embeddings by some interpretable ones, then we can say that this is already good enough explainable diarization. And another general approach that is taken and emerging now is the end-to-end diarization system, where you have your audio file as an input to some black box neural network, which is supposed to give you the solution for the whole diarization problem at once. And this neural network generally is not explainable because even we can extract some internal representation from it, but we don't know what they mean. But we can try to make it more transparent, let's say, by trying to induce some information which we think is meaningful and worth kind of for the model would be good to model. And you will see in shortly how we approach it. And this, if we manage to inject some internal structure into the model, then we can try to interpret the internal presentation from it afterwards. And here I will just quickly show you the baseline results for the diarization systems that we started with. These are agglomerative clustering, as I said, and VBX. And here the results are for two use cases. One's where we use the Oracle voice activity detection, or the other one when we get the output from the segmentation team, and this is our output. And from the numbers, what we can see here, we tested it on both diehard and allies, is that first of all, the VBX seems to be outperforming AHC for both of the systems. But what is interesting is that maybe our voice activity detection is a little bit biased towards allies because we don't see that much degradation in the performance for this data set, while for diehard the degradation is very high. And what I want to point out here is that all of the systems that, all of the clustering-based systems that you are going to see would be using Oracle VAD, so this is kind of the baseline for us. And also, in this case, all of the models are trained on Voxelab 2, and this is the case for all of the diarization systems that you are going to see now. And I will pass the floor to Pauline, who will introduce another clustering-based diarization approach.
Okay, thank you, Anya. I'm Paulin, and I will present what we did during the workshop using graph neural network for the diarization. And as you can see in this picture, we are dealing with acoustic signal. And so, oh, sorry. Oh. 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 I think so. Okay. Sorry. Okay. So here you have the acoustic signal, and as explained by Anya, we will use a sliding window to extract the segment. And this segment, from this segment, we extract the embedding, and the embedding will be used to build the graph. Here, each embedding will represent a node. And we will use some similarity matrix to define the edges between the node, using, for example, a threshold to remove some uninteresting edges. And the GNN model will try to identify the cluster in this graph, and will assign at the end of the process an ID or a label to each cluster. And this ID or label will be used to provide the output of the diarization system. So we have used this GNN model with two goals during the workshop. The first one is to compare the result of this model to the other diarization approaches used by the group, and to look at some post-hoc explanation of how the clustering steps are implemented or processes by the GNN. One, I want to point out that graph, we know that graph are pretty tool to represent the relation between objects. And here, we can see that in our case, we have just used X vector as to define the node, but we can add any kind of information in this node. For example, we can add some linguistic feature, we can add some temperature feature, and define some distances that will be used to build or to generate the edges. So it's very intuitive. It's very intuitive to build the graph using these approaches and use the graph in the GNN model. Again, the same. What is the problem here? Oh. Sorry. Okay, okay. It's so easy to use this. Okay. We use a model proposed 2 years ago by some guys of Amazon, and they have used the GNN model for clustering images, as you can see in the first picture. We have images, and they just they generate a similarity matrix, use cosine distance. And from the cosine distance matrix, they use K-nearest neighborhood to build the initial graph. And this graph is trained using GNN called here Lenders, and Lender is a graph convolutional neural network. And by aggregating some node in the first graph, they will generate the graph in the next level, and then they will train the model hierarchically till they have the last graph. They get the last graph with no more edges. And the ID or the label assigned to the node in the last graph will be backpropagated in the different graph to get the ID of the initial graph. And this ID will be considered as the the label of or the yes or the name of the or the identifier of each person in the first email. So what we did is just to replace the input of the model by X vector, and then define some similarity matrix using, we can use any kind of distance between this X vector as similarity matrix, and we have trained the model, this hierarchical graph convolutional neural network for the diarization. So for experiment, we have used DieHard and Alice, and we have trained the model with 3 setups of the voxel app. The first one is we have used all the voxel app to the embedding to generate the initial graph and then train it. The second setup is we have split the voxel app data used by some file using 300 speakers per graph, and in the last setup we have used a file with 30 speakers per graph. And there are many hyperparameters in this model. The first one is K. The K used to build the KNN graph. L, the number of level in the hierarchical graph neural network. The number of convolution in the GNN, and the graph attention. If we can set the graph attention network, we can say we want to use the GPU on CPU. But we are focused on 2 parameters: K, used to build the KNN, and L, the number of level in the GNN. And we found that this model is very sensitive to the parameter K. And as you can see in the table, the results are not so bad compared to the VBX baseline. And you can see in the last setup give the most the better result, because the number of speakers in each graph is close to the number of speakers in the test set. The one conclusion, the main conclusion for this task is, or for this part of the work, is that GNN model clustering based model can be a good alternative when the explainability is concerned, because graphs are really intuitive. Anybody can build graph according what you want to represent or to design. And there are some, nowadays there are some models proposed to explain the GNN. And these models use some perturbation in the graph structure, and we know that perturbation in graph structure is really intuitive also. So for the conclusion, we'll say that GNN hierarchical clustering provide competitive diarization result. In future, we plan to combine the linguistic information with acoustic information, for example, by using what will be presented in the next section by Feti and his colleague, when they align, they extract some alignment between text and acoustic signal. And adding temporal information still has to be explored. Thank you. I will pass the floor to Victoria.
Thank you, Paula. Hello, everyone. So now, as at the beginning Anya presented, there are another stream of research nowadays, apart from the traditional approaches for speaker diarization, that is becoming increasingly relevant, and these are the end-to-end models for speaker diarization. So this kind of approach consists of training only a single model which solves the complete diarization task. This kind of models has another advantage, that is there is no need of external BAD or an overlap detector, because the system implicitly takes care of this information. But however, these models also has several disadvantages, like they requires a large amount of training data to be able to train it correctly, and this kind of data usually is simulated. And also, when we want to evaluate this kind of system, they usually suffer when we use long files. So in the literature nowadays, people usually evaluate it chunking on source segments and then applying a clustering technique. And also, as you know, in all the fields, usually end-to-end models are black boxes, difficult to explain. So here we want to improve these end-to-end models to encourage the internal representations to be meaningful and obtain other kind of information from it. So here we have worked on two research streams to do this approach. That there are both are here, the end-to-end model plus phoneme loss and the end-to-end model plus speaker loss. And in the future, these two lines of approaches could be joined in the future if we consider that which could help each other. So I'm going to explain both. First, the end-to-end model plus phoneme loss. So in the current end-to-end model, we didn't use if there is some phoneme information inside of the embeddings that comes from the transformer encoder. So we thought that it was interesting to know if there is some information inside. And also if this information is inside in the end-to-end models, if it's helping for the diarization task or not. And then if we check we decide if we push the model to encourage this phoneme information, or it's better to remove this information and push the encoder far away from it to keep more space in the embeddings for other relevant information. But with this, a few days ago, we have some technical and data issues, so we can't show here some results about this. But we are in progressing with this, so we hope we will soon have some results. So in the second approach that we were working here is including, instead of the phoneme loss, the speaker loss for encourage the internal representations. So also, it's the same as happened with the phoneme information in the end-to-end, in the current end-to-end models. We don't know if where we know that there is not good speaker representations inside, so to use for verification task or others. So we decide to try to encourage these internal representations to be meaningful and also containing more speaker information, and also, for example, to improve the ability to discriminate same speaker between different shows or files. To carry out this experiment, this approach, we introduced two different strategies. First, we introduced the speaker loss at frame level, as we can see here. So we introduce a linear layer plus a cross-entropy speaker loss, the typical one. And the second one, that maybe is more and smartest strategy, we introduce the speaker loss at attractor level. These attractors are trained during the diarization, where the diarization system is trained to calculate the number of speakers that they are present in the conversation. So if we put this extra speaker loss, we can see which attractor corresponds with each embedding, each speaker, sorry. But mapping the speaker label, but it has also a disadvantage because it's mapping the speaker labels to know the corresponds with each attractor is also more complicated to manage inside of the system, but we manage it. So also, as I mentioned, an important point to train correctly these kind of systems is the data that you use to train. So for this work, in this workshop, we simulated some conversations of only 2 speakers using VoxTelep. So we simulated around more than 2,000 hours to train these kind of systems. So first, before to go to the diarization results itself, I want to present an analysis that we did with the validation set of this simulated conversation that we generated, and which I'm going to show you a representation of the cosine similarity of 2 segments of the conversations. These 2 segments of conversation has 1 speaker shared between them. And also we did we prepared a protocol of speaker verification to evaluate in terms of equal error rate. So now you are going to understand. So here we can see the cosine similarity matrix. For people who is less familiar with this kind of representation, this first square corresponds to the embeddings of the first conversation, comparing all embeddings between them. And this second score here is the same for the second conversation. So in these two conversations, we can see that inside more or less the terms of the speakers speaking is the system could manage and separate them. But we also wanted to notice here that the speaker C is not present in the first conversation. So this, I forgot, the more yellow is the higher similarity. So we want to that speaker these representations will be lower similarity with these ones. But in this case, as you see, they are higher. But this representation was with the end-to-end model, but if now we include the speaker loss, we can see that the internal separation of the speakers more or less is key, but in this case, we achieve that the system has learned to discriminate that this speaker is not present in the first conversation. We also wanted to see more yellow this part because this speaker A is present here, but well, it's an initial experiment, so we could improve it, I guess. And also, as I mentioned, we ran the verification protocol with the whole validation set to see this in a quantitative measure. So we can see in terms of equal error rate that with the end-to-end model without the speaker loss, we have more than the double of the value than with the end-to-end plus speaker loss. It's a high value, but it's a promising result to continue working on that. And now we evaluated these end-to-end systems also using those two of the typical data sets for diarization, the diehard, that, as my colleagues mentioned, has 11 different domains. And an important thing for the future results is they have 6 domains with conversation between 1 to 3 speakers. And also we evaluated in Allies Clean Test, which has 35 files, 7 files with conversation of 3 to 4 speakers, 70 files with conversation of 2 to 10 speakers, and 11 files with conversation of more than 10 speakers. So now I'm going to show you the results here. As you can see, we are far from the state of the art or the result that my colleagues presented, but we want to see that including this speaker loss, we keep the same or at least the same diarization error that the end-to-end without this is loss, that is our baseline. And also I want to do some remarks about these results, because I want to say that, as I already mentioned, this system was trained without any fine-tuning, so with the VoxLab simulated conversation data, and evaluated. And another advantage of this kind of model was we could evaluate it using the end-to-end model directly, things that in JSALT is possible, that in other clusters is not possible, even with the long files without the need of any chunking. And 2 important issues to remark is the domain mismatch between this evaluation data with the training data, and also the most important for me, I think, is the model during the training is only seeing data with 2 speakers in the conversation, so it's difficult with the files with more than 10 speakers to do it correctly. So we did a deeper analysis, just focusing in the domains with the most similar amount of speakers that we used to train. So here we can see the diehard domains with 1 to 3 speakers, and we also observe that the results are improved in almost all the cases when we introduce this speaker loss to the end-to-end, especially in the case of the attractor level. So and also in some cases it's a huge improvement. So it's the thing that we want also. And also in Allies with 3 to 4 speakers or 7 files, we have also seen the same trend. So we are improving the diarization performance in these files. So we are still far from the good result, but it's promising. And as I did it previously, I put here to finalize 2 representations. This one is 2 files of Allies with 2 conversations of the 3 speakers. And we can see that with the end-to-end model, the system is not able to discriminate between both conversations. But when we included this speaker loss, well, we are far from say that the same speaker is present in both, but we can see how the system is able to discriminate better between both conversations. So to conclude, to conclude this part of the presentation, we will see that it's too hard to manage and train these kind of models. But also we achieved to encourage internal representations to be more meaningful, containing more or extra speaker and information. And for the future work, we plan to follow with this and train the end-to-end models using conversation data with more than 2 speakers. And also we could fine-tune the trained models with domain data and also try different alternatives for the new losses on the architectures include. So now I'm going to give the floor to my colleague to present the low-level resources diarization.
Thank you, Victoria. Hello, now I will be presenting to you the investigation that I've done on the speaker diarization strategy for low resource language. In this case, it's the Sarawak Malay data, which was presented by Dr. Sarah earlier. The approach in particular that is used for this investigation is using auto-labeled dataset as training data, as in the 237 auto-labeled data earlier. So the process is quite simple. Firstly, we obtain the baseline of peer node on transcribed Sarawak Malay data. So we take the peer node model or the p-train X vector model. We perform the evaluation on the 37 test data, and then we use the manually annotated UEM and RTTM to evaluate the diarization error rate, or the DER, which is 15.025%. And this is already good, but can we improve it even more? We'll see. And the next step is to fine-tune the pre-trained X vector model or the peer node model. So the process is to get the DER, the process is basically the same as you want to get the baseline earlier, but the difference is before we get to the evaluation of the model, we fine-tune it first by using the train set. And how we get this train set is by we have the 237 audio data which we use for training, but it's unlabeled. So how we do auto labeling is we use PioNode. We put in the 237 audio files to get the RTTM, and then with this RTTM we generate the UEMs. Then we have the entire train set right here. It's all auto labeled automatically, and then we use it to fine tune the pre-trained X vector model, the peer node model. And after that, after it's been pre-trained, then we do evaluation on the same test set that we used to get the baseline earlier to see the performance. Then we get the diarization error rates. For the sake of investigation, I separate the training data, not really separate, but more like I sequentially add more and more of it. At first, I start with only 20% of the training data. Then I do fine-tuning and evaluate. But then I repeat the process again with 40%, and then 60%, 80%, and 100%. And this is the results that was achieved. And as you can clearly see there, the baseline 15.03 or 15.025 with 20%, and it gradually gets lower and lower, which proves the hypothesis to be correct, that the amount of training data that we put, the size of the training set does improve the diarization performance as the DR gets lower and lower. Now the conclusions that I have for this is that, as I mentioned just now, the size of training data affects the diarization performance because the diarization error rate gets lower and lower. And the next one, the unlabeled data can be used for fine-tuning without having to do any manual annotation, because the manual annotation is only done on the 37 test set, and there was already long been, the ground truth already long been obtained. On the 237, it's all fully automated, the RTTM and the UEM. So because of this, it opens more opportunities for to look into the unlabeled data side. How can we use it even more for improving diarization? So that's why the future work is one of it is to investigate pseudo labeling, the concatenation of Sarawak Malay speech data. This idea is given to me by Sanjeev, and that's for and also the unlabeled data. The thing about the 237 unlabeled data, that's only for one language, the Sarawak Malay. I use that language in particular because the test set we tested on Sarawak Malay to evaluate. But what if we use other languages? Does it also improve the diarization? We'll see, because in the website where I'm getting all the Sarawak Malay data set, there's a lot of languages, not only Sarawak Malay, but many others, and there's thousands of them. And other than that, more labeled data will also be coming in soon. So in a way, I can compare. Is it really better to use unlabeled? But what if I use labeled data as well? Will it improve the performance even better than unlabeled does? Now for the takeaway for the diarization team, is it possible to build an explainable and well-performing diarization system? And as they presented earlier, the two approaches are to firstly to change the input of existing diarization to a more interpretable one, or just modify the approach altogether. And other than that, the clustering baseline approaches perform the best even with interpretable input embeddings, and this will be shown later. And this is good in both performance and explainability. And the third takeaway is the EE&D models are difficult to train and experiment with, and they also are time-consuming from what I heard. But there is a good indication that with additional information injected in the model, they get better in performance and explainability. So, any questions?
So I guess this question may be for Victoria. I don't know who it's for. If you could go back to the slides where you put this speaker. Yeah, any one of them is good. Yeah, this one's fine. Or maybe actually go to the another one which had 3 speakers ABC. Yeah, this one, right? So it looks like by adding the speaker loss, you're hoping to improve finding of speakers across conversations. But what you seem to be accomplishing is rejecting any match between conversations. In other words, you managed to make it easy to see that C is not present in the first conversation, but you also managed to hide A between the 2 conversations. So in some sense, looks like what this is doing is it is helping you reject matches across conversations and not really find speakers across conversation. Is that a fair criticism of this result?
No, but one thing that we saw that we are rejecting the speakers when we want to increase also to find one in the other conversation. So that's one also the problem though, that we have this higher equal error rate because we are missing the positive speakers in the conversation. Yeah. So it's a thing that we have to try to investigate and improve it. They also remove ones and keep the other ones.
Right. So I wonder if rather than using something like binary cross entropy to say this is the same speaker, whether you need to have some kind of ternary thing where you say there's the same speaker in the same conversation, there's the same speaker but in a different conversation.
We are using a multi-class cross entropy, so it's not binary. So it's
whatever, whatever you use. All I'm saying is you're telling the system that on the top right box, the speaker in the first conversation and the speaker in the second conversation are the same, right? And in the bottom right box, you're also saying the same thing. This is the same speaker. Yes. What I'm saying is those could be 2 different targets. Saying this, in other words, instead of saying same speaker versus not same speaker, you have not same speaker, same speaker in the same conversation, same speaker across conversations. Because there might be some effects which need to be discovered specifically across conversations.
Yeah, it would be nice to have two different labels for the same speaker, one in the same conversation and another in. Yes, you are right.
Thank you guys for very nice presentations. Actually, this is a question to Paulin, sorry, about the GNNs. So your states in the network were just attributed to single speakers, or can you also work with overlaps of speakers in your analysis? And if not now, are there any prospects to work with overlaps in the future?
In the model, we are using overlapping in the. Yes, we can extract, we can use overlapping segments because we are just using a sliding window and extract embedding. It means that, for example, if we have two nodes representing one, for example, the non-overlapping part and another node with overlapping part, the distance will be low compared to the distance of two embedding for the same speaker. So the edges are weighted in the graph, so we can use this information to infer some. I don't know if...
okay, but have you done it so far, or is it just the pure speakers and this is just a planned work, or was it already done?
Yes, it was already done in the...
Okay, thank you.
For the test, for the test data, in the test data.
Thank you. I have one more question, if I can. This is more for the beginning part, for the feature extraction. I think it was for you, and I'm sorry, I don't remember the name. Yes, the guy, the stripped... T-shirt. No. No, for the guy sitting here. Yeah. So sorry, I should learn the names. It was about the energy features. So basically, these can be very crucial for determining like who is this more louder speaker and softer speaker and so on. And you said that you are using the deltas or derivatives of energy. But then you can do lots of different normalizations, like before it, after it, global, local, speaker-based one, whatever. So what is the best practices to do normalization in the determination of energy for this task?
So we didn't, in our group, on the features, we didn't work on the speaker, on diarization. We wanted to get speech, not to discriminate speakers against one against each other, except in the overlap part. But what we used were baseline the acoustic features we were using. Mainly, we were removing the energy from the MFCCs. So the first one, the first component. As for the at least for the overlap part. The other MFCCs were more discriminative.
Okay, but then I think someone mentioned using the energy and not the base one, but the derivative of the energy. So I just wondered, like, what was the normalization deployed? But maybe it was not you, but the speaker that spoke before you. I'm really sorry, I don't remember. Energy. Maybe we can take it offline, actually. If it is not clear, I'm not going to delay the whole show. Thank you.
Thank you.
All right, so good morning, everyone.
Sorry.
Yeah. Sorry.
Roger Moore is saying that he's quite confused about what would constitute a good explanation for diarization, given that diarization is itself an explanation of an audio stream.
So yes, of course, the diarization gives some segmentation. So you have the boundaries and you have the speaker IDs, but you don't know why the system, the diarization system, has put this boundary here. Neither why did it cluster two segments as the same speaker. So we can extract from the diarization system some information to explain the decision. But that's what we are investigating in the project, in fact. I hope it answered to the question.
right, so good morning everyone. I'm Suhaila. We are from the speaker change detection from linguistic transcriptions. Yeah, okay. All right, so the goal here is to detect the speaker change, and then another keyword is from the linguistic transcriptions. Right. So to answer these questions, can linguistic information help to explain speaker diarization? So these are our main questions in the team. And then to answer these questions, we have applied to two approaches. The first one is mainly on the motivation itself. Is this the output from this motivation could lead to the next steps in step 2 and the step 3, whereby the step 2 is mainly to predict the speaker change using the transcriptions, and then the transcriptions here is mainly on the reference and hypotheses, and then the follows steps would be the integrate how we can integrate the speaker change information in ASR training. So the motivation here is to investigate the relationships of the speaker distributions versus lexical contents in the French broadcast news is limited to the spare-aligned data. All right. So how did we come up with this? We did this investigation is from the identifying the speaker of each segment using a clustering, and then from that clustering we observe the patterns from the speaker clustering based on the semantic understanding. So this is the pipeline that we went through, whereby in this pipeline, we are applying the translation text, and then for this translation text, you're using reference data and also the ASR hypothesis, these two types, and then we went through the segment embedding, and then for the segment embedding, we're using transformer-based learning, and we go through the clustering. For the clustering part, we're applying to a hybrid approach, we could say a hybrid approach, whereby we're using the bird topic here and the k-means. The purpose of using the bird topic is, this is mainly on the topic modeling, just applying, is to get the idea of the similarity context in from the segments, and also we did the clustering using the k-means here. And from the pipeline, okay, we obtain these results, so-called these results, and then based on the two scenarios. The first scenario is based on the one show. So to answer this one, in one show, the purpose is to see which speaker occurs more than one time during one show, to see if there's any overlapping speakers. And then if you can see from this plotted graph, the dotted colors is representing the speaker ID, and then from these two plotted graph, it shows that there's a similarity, between these two graphs, whereby from these two clusters, speaker 1 and speaker 2 is like dominant in the cluster, similar to from the ASI hypothesis, whereby these two speakers, also the same speakers, are dominant in the clusters. All right, and then in the next scenario, whereby this is mainly on the merged shows, meaning to say more than one shows. Okay, we're trying to look into who spoke more, who spoke in a similar context. So in the similar context here, we didn't go deeply into the linguistic part, the deeper part of the linguistic level, but we look onto the similar context of the, based on the segment discussed. So here, from the reference data that we have, it clustered, produced three clusters. And then from the ASI hypothesis, it produced 5 clusters here. So there's a difference here. We could see there's a difference here because in the ASI hypothesis, there might be there's a possibility of one segment it's not been decoded compared to the one segment in the reference data. So this is what we could see from these observations. And then from here as well, we could see that there's a possibility of the speaker change occurs based on this scenario. So based on that one, based on this investigation, so we proceed with the next steps, whereby we're trying to get the speaker change detections using the transcriptions, and then the next method. So I pass the floor to Tian Ping. Thank you.
Hello, good morning, everyone. Okay, I will discuss our work in doing speaker change detection or speaker boundary detection. Traditionally, speaker change is a task in speaker diarization, is a subtask in speaker diarization. So normally it's used, we use acoustic data to do speaker change and speaker diarizations. And in this task, we are using linguistic information, particularly with the output from the ASR. So we are using the output from the ASR, which contain text and also some phonetic information as input to our model. So the task of our model is to identify the token that will tell us that there is a speaker change. Okay, so to do that, we have a classifier that will identify which token tell us that there's a speaker change or boundary. To train this classifier, we have automatically annotate label the data using the speaker diarization corpus. So from the speaker diarization transcribed data, we know the time where a speaker start and a speaker end. So this information will help us to label which token happen to indicate the speaker change. So when there is a speaker change, we will label it as 1, otherwise we label it as 0. So our model is trained using, we use a large language model BERT, and then fine tune it, and on top of it, we have a classifier that will classify the token, whether that token indicate a speaker change. So this is the result that we get. We perform two baseline, we have two baseline models. The first baseline model used the reference transcription, and then we use a Montreal force aligner to align, and then to train, and then test the model. And also, we also have the diarization output, and then we use it to calculate the speaker change for this baseline speaker diarization results. And for our task, we tested two ASR decoder, one using Whisper X with wave-to-wave alignment, another wave-to-wave, another Whisper with DTW alignment. So, these are meaning these use the output from the ASR decoding for training and then testing. And we have evaluated the model using two different metrics. One is token-based metric, another is time-based segment metric from PioNode. The token-based metric basically calculate whether we get the speaker change token correctly. So we calculate the precision and recall. And for the time-based segment metric, we calculate the coverage, purity, precision, and recall. And at the end, we also calculate the average of these four metrics. And if you look at the result, you can see the first one is the baseline result we get using the alignment, using the reference transcription. It performed best at the coverage. Okay, and also for the diarization system, we use the Oracle voice activation detection plus VBX. The result shows that it performed best at the purity and also recall. And for the Whisper plus DTW, the results are more or less average compared to other models. And for the Whisper X plus wave-to-wave, we get very good result for precision and recall for the token-based metric, and the best result for the precision and overall results. If you look at coverage, purity, precision, and recall, and the result is actually if you compare with diarization, they are quite similar, only slightly better. So this is a surprise for us, since it shows that using linguistic information alone can perform on par with the speaker diarization system. So we perform some simple analysis on the unigram token, top 10 unigram token of the speaker change. So these are the result obtained from the force alignment with the Montreal force aligner. So this in descending order. So this U is special label. We label it for the silence or noise at the start of an utterance. Okay, so other tokens are just lexical tokens. We also perform analysis for the whisper X, ASR, the unigram tokens. So these are tokens based on some word unit. We also have the migram from the Visual X analysis. And this is the visualizations of the reference. So the dot there indicate a speaker change. So, and also this is the result from diarization VBX plus VAD. And this CSG tell us the speaker change with the Whisper X model that which performed the best. And the pink box shows that the place where the speaker change produced is better than diarizations. Okay, so and we magnify this part here, and this shows that in some cases, the output from the linguistic speaker change can perform better than the diarization system. And using linguistic information, as I explained just now, could produce better information in some cases, and this can help. We can use it with maybe human annotator to make decisions, for instance, or probably in the future combine linguistic speaker change with the diarization system. I will pass it to Fatih to continue.
Thank you, Chimping. Hi, I'm Fatih and represent the next part. So, contrary to what Chimping did by using the output of a SR system, we also tried to include actually the speaker change detection in the speech recognition itself, task itself. So what we did here, we said why not train an SR system to transcribe and predict at the same time if there is a speaker change, yes or no. So as presented in this picture, the system will be trained in a fashion when there is multiple speakers per segment, and we would like the system to, at the end of the first speaker turn, produce a token that will tell us that there is a speaker change, and then continue the transcription for the next speaker. So we did this using speech brain toolkit and trained on ALICE dataset and evaluated on ALICE dataset. Here you have some statistics. The baseline system and evaluated on word error rate on ALICE clean, and the word error rate of the system after this training with this speaker change fashion. So here you can see a drop in the word error rate before and after including 2 speakers for some segments, because we were not able to include 2 speakers for all the segments. You have here the number of encoded segments compared to the number of segments, but we have running experiments that will narrow a bit the difference between the word error rate before and after. So in order to evaluate this, we did 2 mainly evaluation in addition to the word error rate. The first one is the purity by detecting if inside one segment we have only 1 or 2 speakers, but the detection done by the ASR system itself. And as you can see here is the F1 micro shows that the system is good compared to a baseline where we say that we have always 1 speaker, which is usually the case when we train ASR systems. So we are good at detecting segments that contain more than one speakers. We then focus on the segments that have 2 speakers, and we were able to detect at more than 53% and 51% for dev and test respectively. And most of the problems we have is the wrong position of detection we detect there is a speaker change, but we detect it at the wrong position. So we are aims to work more to correct this detection. So to conclude this section, I try to be fast a bit. To conclude this section, we started from the idea to study if we are able to detect speaker boundaries using only linguistic informations. We were able to detect this by using actually a training system based on the transcription only, and integrated this in a task done by the speech recognition system itself. We also investigated large language models to be trained and fine-tuned to detect speaker boundaries without any clear conclusion, but we will continue to do this, and in the future we'll try to include more linguistic information, mainly by using, for example, part of speech tag in addition to the surface form that we do use until now. So that's the conclusion for this part. If you have any questions, we'll be happy to answer. So I think we will have a break after this part. So questions before the break?
So thank you for the last part. How do you represent the speaker change or speaker identity in the ASR output? Do you have some speaker change tokens or labeling the words with speakers? And again, my usual question, can you handle speaker overlap?
So we didn't really include speaker overlap in this, but generally if you see how ASR data are annotated, they are segments, 1 speaker per segment. So what we did here mainly is to encode the signal and put back the next speakers to be decoded in the same segment, and in the linguistic or the manual transcription side, we put a kind of token, speaker change token. So to be included in the vocabulary mainly.
If I can add something, I'm not in the team, but I know that for the data we have, sometimes I think we cannot have the transcription when you have speakers overlap, because sometimes you have more than 3 speakers speaking at the same time. So it's just a mess.
But we'll give it a try.
Well, should I start? Yeah. Okay. I'm Lara. I'm going to talk about continuous emotion detection. I work with Haptanto. So another characteristic that we can extract from the audio is the emotion that the person is expressing in this moment. We can use only speech information to have this data. And this can be useful mostly for the output of the diarization part, because we can check if the diarization system make a mistake labeling a speaker. We can see if the truly speaker maybe change the emotion at this moment in the conversation. So with this in mind, our main goal is to develop a system capable of detecting the change in the emotion that a person is having during a conversation. For that, we use 2 datasets. One is the mocap that consists of 12 hours of speech from 10 different actors, and the other one is MSP podcast that have more than 100 hours of speech from more than 1,000 people. Sorry. So for both datasets, we have 2 different labels. One is categorical, that consists of the common emotion, anger, frustration, fear, surprise, and so on. And the other one is dimensional labels that the annotator, using the self-assessment mannequin, they choose, in case of activation, the intensity of the motion that the person is having. And in case of balance, they choose how positive or negative the motion is. So first, we start developing a classification, working in the classification tags. That means using the categorical label. We use only the YEMOCAP dataset with the label of anger, happiness, combined with excitement, sadness, and neutral state. We use cross-validation for testing, taking out one session at each fold. And we also try using normalization and not at speaker. The normalization was done at speaker level. With that, we were able to get the state of the art using the OpenSMAL feature set that consists on pitch, loudness, jitter, shimmer, and the common one. But then if we use embedding that were given by the pre-trained model, like Wab2Vec or WALBLM, and we change the model for a simple CNN, we get a higher, better performance. So our goal was to try to mix different data sets, and to be able to do this, we decided to move to a regression tag using the dimensional label, because it's much easier to combine, because the annotator almost have different definition of the categorical label, so it's difficult to join them. So for that, we use the two datasets, YEMOCAP and POSCAD. We use the same model as the classification tag, but we train the graph function to use the concordant correlation coefficient. That is one that is being used in the literature now. And also this one was used to present the metric for this system. Another thing that we apply is that the input, where the model were fed with the audio, we choose only the first 60 seconds of the audio. If the audio is longer, we cut it. If not, we pass with 0. Something, well, we can see on YEMOCAP, we get the same result that was expected for this dataset. In case of POSCAD, it decreased a lot, but we can see that the normalized option is good for the system. And something that I would like to highlight is that we combine YEMOCAP and POSCAD in the training set. For testing, we only use POSCAD, so the first and second plot is compared to each other between them. We can see that the performance of the system didn't change too much, so that is good for us because we can continue analyzing this type of combination. We should continue working on that. The same, oh, sorry, I completely forgot that was for activation annotation. And the same, we apply the same system for the balance annotation, and we get the performance decrease a lot, but the conclusion at the same. We can also mix both datasets, and we don't make the system much worse. So our annotation consists of one score at each segment. That means we have a speaker in only one at the segment, and the annotator choose one score for this segment, like a summary. But we would like to use this system in a continuous detection. So we would like to have more than one score at the segment. So we change the model to use a sliding window with overlap. So because we would like to have much more information at each segment and not only one score. For that, we choose, for the training part, we choose randomly a shorter segment of 4 seconds. In the literature, it has been proved that it's not necessary to use the entire audio to get enough information for this tag. For the testing, we use a sliding window for 4 seconds with 2 second overlap. And here we can see the result for the normalization model, the orange at the previous one with a 50-second length, and the other one is with 4 seconds. And we get the models are same or slightly worse, that is not significant. So that means it's not necessary to use the entire audio to be able to solve this tag. So this is an example of how we would like to use the system. This is an example using a model that was trained with YemoCap and PostCat and with the feature set of WebLM. We can see that the score that was predicted by the system are in the same range that the one that was predicted was annotated by someone before. So our main goal was to develop a system capable of detecting the volume and emotional time of a speaker during a conversation. We combine different data sets, and we can see that it's not worth the system performance. And also we short the segment of the input, and we can see it's also enough for this task. What we need to continue doing is train more combination of YemoCap and PostCat. I mean, testing only in YemoCap or only in PostCat, but training with both of them to see how to check the robustness in the out-of-domain tag for our purpose. So also we would like to include another dataset like CIWA, MVP improve, and continue shorten the segment to see until we can reduce it. So, question until now? Okay, so I continue. So another thing that we would like to show is a little demo about all the topics that you can hear until now at this part of the talk. So we choose one audio of the allied dataset randomly, and we see what happened with the output of each of the systems that every group has to play today. So I would like to show. Yeah. Okay. So the first plot is the reference, that means the ground truth. It was labeled manually, so we can see when each speaker is talking, like when it's speaking. The second plot shows the output of the segmentation system that shows us when we have music, noise, overlap, and speech. And the last one is the output of the diarization system that shows when we have different speakers. Something I would like to highlight is that the diarization system at this time, I don't know, at this time, after the 100 seconds, make a mistake. He tried to add another speaker, and if you see the segmentation output, we can see that at this moment, the audio starts having some music. So we can explain the behavior of the diarization system using the segmentation. Another output that we can check is the speaker chain from text, and we can see also on the same part that it truly is predict correctly or defined correctly when a speaker is going when the speaker is going to change in the conversation. We can see it a bit before than the reference part, the annotation. Another thing that we don't explain this system, but we have it, is like the name entity recognition to identify exactly which speaker is speaking in this moment. And we can see that Lionel Thompson was correctly identified at the same time that I have showed the previous example, that it's the same speaker that we have at the reference part. Well, another thing that we can use is the output for the arousal and balance prediction, and I have no conclusion about this part because it's necessary to have more conversation, and maybe more useful when you have two speakers than so many. So no, coffee break, no, we already have.
Thank you, Laura. Okay. So hello, I'm Antonio, and I'm going to start explaining some of the methods that we have followed to explain models and their decisions. So first, I'm gonna start presenting what I've been doing with Alfonso. Our goal was to have a model that worked well in different tasks. So we divided both in regression and classification tasks. And also, additionally, we also wanted to have some explanation from that model, or the outputs of that model at least, So the method that we followed for that was to have a latent space representation, but with a set of constraints that we impose by design, which hopefully this will allow some degree of understanding or explanation. So first, for the regression task, we propose to use a variational autoencoder, but with constraints in the latent space. So we define two independent latent distribution, one of them which corresponds to information that we know, which means that it's labeled, or at least pseudo-labeled, and the other one corresponds to information that we don't know, which means that it's unlabeled. Since we assume that these two latent variables are independent, we have that the large function is the reconstruction term, and the sum of these two KL divergences, one of them corresponding to the output of the encoder corresponding to the label latent space and the target latent distribution, and the other one the same for the unlabeled latent distribution. So I'm going to show you one application of this method. So this, we're going to try to use it to do domain translation. So first, to initialize, we first define a base target mean, which we define randomly. After that, we define as many rotation matrices as classes we have. And after that, we obtain target distributions per class, different target distributions per class by multiplying the previous rotation matrices by the base target mean. And then we get these means, and then after that, we assume, we impose that the distribution, that the target distribution is a normal distribution with the mean that I explained for an identity matrix as covariance matrix. So after that, once we have trained the system by trying to minimize the last function that we can see in the slide, we have that given an input X, its class C and a target class T, we first get the two latent variables, the label and the unlabeled one. After that, we rotate the latent space to the target class by multiplying to the inverse of the rotation matrix corresponding to the input class. After that, we get this like base latent variable. And after that, we multiply that base latent variable by the rotation matrix corresponding to the target class. And after that, we pass the label latent variable and the unlabeled latent variable that we didn't change at all through the encoder, through the decoder, sorry. And we get some of the results. We did some experiments that I'm going to show you now. The first of them was with the very well-known dataset MNIST. Here we have some numbers, and we want to translate, to change the digit, but keep all the information which is not the digit. So in this case, it would be the thickness, the inclination, summary, everything which is not the digit. And as you can see here, we are able to more or less keep the same style, but having new digit. So on the left, we have the original image, and all the right images correspond to an image created by our variational autoencoder by modifying this latent space. So here, other example with the Street View house numbers dataset. Here, our goal is to keep everything which is not a digit again. For example, in this case, it would be a color, some extra digits, the inclination of the digits as well. Here we can see also a very interesting thing, which is that in some images we have more than one digit, but the model knows that it only has to change or to modify the one which is in the middle, because while we were training the model, the labels corresponds to the digit which is in the middle in those images that have more than one digit. So here, this final example is we try to rotate cars. Here, the idea is to just change the angle of the cars, but keep the same color, the same car model, also the shadow, if we have shadow. So here, the input is a car in a given angle, and we want to modify that angle, but keeping keeping the same car. So on the same color and everything. Here you can see that it works quite well. So sadly, the goal of this workshop is not to rotate cars, so we have to switch from vision to audio data. So here we find two more challenges. One of them is that we have to model sequences, and also we can have inputs with different lengths. So the first, the application that we did was instrument translation. We did with this medley solos DB dataset. The problem with this dataset is that we have less than 20 minutes for every instrument which are not piano and violin. So we only took piano and violin. We have around 2 hours of each instrument, a bit less. And we took the spectrum, we passed it through the TCN encoder, we modified some of the label latent variable to make the translation. We pass these latent variables to the TCN decoder to get a new spectrum. So here, as you can see, I show you some of the reconstructions of the translation. As you can see, the reconstruction is not perfect, but it's like a kind of filter version of the input. But we are going to try to listen them to see if some of them, just to see if how they listen. This is the original. Now I'll show you the piano and the violin translation. As you can see, it's a kind of filter version of the input. This is like, this should be a violin. Let's listen some more examples. Now we will listen some examples in the other way, from violin to piano. As you can see, it sounds, the problem when we are going from violin to piano is that in this data set, the notes in the violin are very long, and we are not so used to listen so very long notes in piano, so it sounds, it doesn't sound very natural, but I think that it sounds more or less, at least the first part of the notes, more like a piano. So the goal again is not to translate instruments. The actual goal is to have an explainable diarization system, and for that we want to have an explainable speaker characterization, and for that we're going to try to build an explainable classifier. So to do this, we are just, instead of having a variational autoencoder as we had for regression, we are just have a variational classifier, which is just, we have the same encoder in the variational autoencoder, but we just substitute the decoder by a linear layer and softmax because the task actually is classification. And also we are going to impose some constraints in the latent space. We'll have also two independent latent distributions, one of them corresponding to the label, to the known information, and the other one corresponding to the unknown information. And here the last function is the same, but instead of having this mean square error as in the first term, we have the cross entropy because the actual goal of this task is to do classification. So here we have an application that we did with this system. So this application was to have an explainable classification according to a set of attributes that we define as first input. After that, once we have defined what attributes we want to explain, we define a distribution of the latent space that depends on these attributes. So again, once we have trained our system, we want to explain the output. So the first step is that we can understand the latent variable, because since during the training we wanted to minimize the KL divergence between the output of the label latent variable in the encoder and distribution that depends on the attributes. So if we sample from the output of the encoder, that embedding or that variable should contain some information on the attributes. And furthermore, we could also try to understand the model, or at least the last layer of the model, since the predictions are typically obtained applying a linear layer and softmax to the latent space, to the embeddings in this case. So the relation between the label latent variable and the predictions can be analyzed to get some information on how these attributes and prediction are related. So we did like a very simple experiment with the mockup, trying to explain how different attributes that we define are related to the emotions. So here we chose F0 medium, F0 standard deviation, and loudness. So after that, we got, after getting those attributes, we got the 33 and 67% for each of them. So while training, we discretized the attributes in low, medium, high according to the percentage we calculated before. And after that, we defined the target distribution for each attribute by using one-hot encoding. For the mean, as I show here, we have 100 for low, 010 for medium, and 001 for high. And then we assume that the distribution was a normal distribution with that mean and identity matrix as covariance matrix. So here we show, I show some of the results. In the first row, we can see the joint probability of each emotion and each of the levels of each attribute that we wanted to explain. And in the second row, we have the weights of the last layer, which connects the component corresponding to each of the level of each attribute to the emotions. And here we can see some interesting results. For example, in the case when we have high loudness and angry, we have that the joint probability of these two, of this attribute level and emotion is very high. And also we have that the weight that relates this high loudness to the angry is high, is positive and high. And the one that relates the low loudness and angry is negative and the most negative actually. Something similar we can see for example, for the case of high standard deviation pitch and happiness. And yeah, so we can extract some information directly by analyzing the weights of the last layer. For example, we can also see that the less relevant attribute is the F0 medium, and this is something that we can just see by checking the weights of the last layer without doing any analysis of the trained dataset. So finally, I show you the last application, which was to have this speaker characterization depending on the environment, which in some sense is explainable. Here we have 2 extra challenges as well. We can also have variable length input, and we can also have different classes in train and test. So for that, we first initialize we define first a set of attributes describing the environment, which could be the output of, for example, a multitask segmentation system or the type of augmentation used during training phase. After we define this set of attributes, we define a distribution of the latent space that depends on these attributes and each speaker S. So once we have trained the system, we want to know if given 2 inputs, we want to know if they correspond to the same speaker or they don't. So we calculate the mean of the label latent variable for each audio. And after that, we calculate the cosine similarity as a score. And this could be the typical score, but we also want to explore in the future some other metrics, taking the advantage of having distribution in the latent space instead of having just one embedding, such as, for example, we could use this symmetrical divergence between the 2 distributions. We could also use other metrics, such as cross entropy or Bayer score, something like that, to compare the 2 distributions. Finally, I'm going to show you some of the results, some of the experiments we performed, and some of the results. For that, we just took a kappa TDNN system, and we just switched that arc phase layer loss by this cross entropy and KL divariance. And we trained the system with VoxLab. So here we have maybe the 4 most important experiments we performed. The first one was the non-explainable baseline, which was using this R-phase softmax. The second one was by defining the mean of the target distribution depending only on the speaker and make that mean trainable. As you can see, and we didn't use that extra unlabeled information for that extra dimensions for the unlabeled latent distribution. So as you can see here, the results were worse, and in the baseline it was a bit worse. So in the next experiment, what we tried to do is to, instead of making the means trainable, we made them to be as separate as possible. We made them to be quasi-orthogonal. That the point is that the means of different speakers should be as far as possible in the latent space. We didn't use dimensions for the unlabeled latent distribution either, and we got here better results than in the previous experiment. These one are closer to the non-explainable baseline. Finally, in the next experiment, what we did is to define the labeled latent space in the same way as in the previous experiment, but we added those extra dimensions for the unlabeled latent space. Here we got a bit worse results than in the previous case, and one of the things that we didn't like a lot is that we got that 5% for the unsupervised, for the unknown label latent distribution, and we would like to get a very high equilibrium rate because ideally we would like not to have information of the speaker at all in that latent distribution. So finally, the next thing that we would like to try is to make the target distribution of the label latent space to depend also on the environment, and the idea that we have for that is to just have this means that depends on the speaker and rotate something in the space depending on the environment. If we have a speaker here, we want to rotate in some angles. If, for example, we have music background or in the background, or rotating other dimension. If we have background noise, and rotate it more or less depending on the noise level. But we don't have results yet, so we hopefully will have something in the future. So finally, as final conclusions, we first divide the latent space into known and unknown information. We can make the non-latent space depend on some attributes. We have also demonstrated that can be useful for domain translation, for explainable classification, and speaker characterization as well. And a future experiment, we want to have a speaker characterization depending on the environment, which in some sense we could say could be explainable. So thank you.
Hello, so it's me again. And I'm going to present our work that we did with the experiments with incorporating the uncertainty information into the embeddings, as the embeddings are used by most of the diarization models. So this, we think, could be beneficial. And the work is based on a very simple idea that one shouldn't trust the embedding extracted from short and noisy recording as much as the one which was long and clean. So in the latter case, probably there is more speaker information that you could build your embedding upon. And to pursue this idea, we were very much inspired by the XI vector approach that is described in this paper, or introduced in this paper. And here, what it does, basically, they are just, instead of estimating the embedding as a single point, the embedding extractor is supposed to output a posterior distribution of the embedding, and in this case it is modeled by Gaussian distribution, where the original embedding would serve as a mean of this distribution, and the precision, which is precision matrix, which is just inverse of the covariance matrix, actually reflects the uncertainty about where the true embedding is if you have infinite long clean recording. And in this model, the precisions are estimated on frame-by-frame level, so we can track this uncertainty in time domain as well. And here is just a very quick recap of what this model does. So if you look at the picture, basically, if we ignore the things which are in this dashed line block, this is a standard embedding extractor. You have some encoder pulling few layers after the encoder, and you extract the embedding. What makes it the embedding with uncertainty is this additional branch here, which is supposed to extract the precision matrices for each output of the encoder. And okay, maybe I'm not going to go into much details about the generative model, but what is important here to notice is that by defining some generative model, we directly get the formulation of how the pooling should be done, if we believe that this is the correct model. And also, we know how to summarize the precision, so basically the certainty about our embedding across the whole utterance. And the model is nice, but so far it's not very logical why it should produce you some reasonable precisions, because it's kind of it's trained with normal typical speaker loss, which does not encourage the output of this extra branch to be good precisions. So we wanted to examine a little bit what actually it produces, and here's one example. So here, what I was doing is I take test set of voxelab1 and extract the precisions for it. And here you see the histogram in blue of these precisions for voxelab1 when I used the original version. And then I also augmented it with some additive noise and extracted the embeddings again. Or not the embedding, the precisions. And the orange histogram corresponds to the precisions of the augmented version of voxelab1. And here we can be a little bit happy that the orange histogram is shifted to the left compared to the blue one, meaning that on average the precisions are lower when we have more noisy utterances than the original ones. Another thing that we can take a look at is this temporal precisions, as I said. So here, the black line on the plot corresponds to this precision extracted every 80 milliseconds in our utterance, and the colorful lines are the output of the segmentation model from our team. So basically here, what we would like to see is that when we observe that any of the colorful lines are high, so meaning that, for example, there is high probability of noise or overlap, for example, then the precision should go down. And probably we see the strongest in case of like when the segmentation model doesn't find any speech, then we really can observe that the precision is lower, which is probably what we expected. So now we kind of verified that the precisions are more or less reasonable. And these are some results that were obtained with this model. So here we see 3 different models. One is the traditional embedding extractor, which doesn't use any uncertainty information. Then the second one is basically the baseline xi vector. And the last one is a little bit smarter at xi vector in the sense that it uses the precision extraction branch uses additional input, which at training time is basically SNR of the additive noise that was used to augment the training data. And at test time, this would be the output, also like the posteriors, as I showed before from the segmentation team. And we see that for speaker verification task, the models that use precision manage to improve a little bit the results over the model that doesn't. However, the improvement is kind of marginal, you would say. And for the diarization, we compare the same 3 models. And here, the last, like the start numbers are the last minute numbers, so they are not completely trustable, so I would take them with a grain of salt. But otherwise, we would see that for diehard at least, the precision, including this precision or uncertainty information, helps to improve even the diarization results. And just to have some intermediate conclusion, so why do we care about instructing these uncertainties? Because it provides the user with a way to estimate how confident the model is when it provides its decisions, and it's beneficial, for example, when doing error analysis, and also can improve the diarization performance itself. And in future, we think that it's a good idea to modify the model so that the uncertainty estimation that we get from the model are more sensible, for example, by introducing some specific laws which would encourage the behavior that we like for these matrices. And also, we can incorporate these uncertainty estimates into the clustering algorithm itself. So this is it for me, and I pass it to Mari. Thank you.
So now I'm going to present another way to constrain the latent space using mainly sparsity and non-negativity. So for example, the idea is that if you want to give a characteristic of Le Mans, you're not going to describe the presence of bridges, river, and medieval city, but you prefer to say that there is the 24-hour circuit. You may not say that there is no Eiffel Tower. This is not very informative. Regarding speech, you can say, for example, that there is presence of some phonemes, some silence, or some acoustic information, but this is not really characteristic. Maybe if a speaker has a strong regional accent, it will be more discriminant, and you will probably not say that there is no low F0. So this motivates the use of sparsity and non-negativity to constrain the latent space. So to do so, we have trained an autoencoder that doesn't compress the information, but in the contrary, will spread the information in the middle. So we train it on top of X vectors. We have 3 losses. One is the reconstruction loss, and the 2 other enforce the sparsity of the embeddings. And we enforce also the fact that they are non-negative, so we have a capped ReLU loss function. So we can see here how many 0 and 1s we have in our spine vectors. So the baseline is 137 for ER on VoxLab1, and we check that we do not degrade too much the results with our spine vectors. So these are real values. We can see the number of 0 in blue and the number of 1 in red. So the number of gray values are in between 0 and 1, and they are becoming 1 when we are going to binaries these spine vectors. And we have here 3 different values of sparsity. So 15, we have very low value of 0, and 70% we have a large number of 0. So we can see that we degrade the ER, but so far the 3.15 ER contains a lot of 0. So we have made a decision with very few ones. So we have checked if this constraint in the latent space do not degrade the performances on several tasks. So we have tried on ER. We can see that, so I already showed the result, but we can see in red that the binarization doesn't degrade so much the results also in comparison to the real values. We have compared also the diarization performances on these 3 spine vectors. And even if the spine 70% degrades a little bit the ER values, we continue to have, we maintain the performances in terms of GR. So it means that the information maybe we have removed for speaker verification is not useful for diarization, so maybe environment information. And we also checked that we have no degradation on 2 classifiers, so gender and emotion. Regarding gender, we can see that we have good performances either with spine or with binary spine vectors. And regarding emotion, so we have a small data set, so it's not very easy to have generalizable the results. But so far, the binarization seems to degrade quite a lot on the 15% spine approach, because in fact you have a lot of values in between 0 and 1, so maybe these values are informative for emotion classification. But with the very sparse and binary vector, we have quite reasonable results. So this means that we can continue to work on this spine version, so to constrain the latent space to be binary and sparse. And we then have tried to make this link between the representation space, so our spine vectors, and the informative world.
It's okay. Hello, I am Imen. So as a continuity to what Mary presented, here the goal is to investigate the representation world, which is the spine vectors, and get the most relevant dimensions with respect to 2 specific tasks, which is emotion and gender classification. So as a first step, we did dimension selection using 3 methods. The first one is with a simple classifier, and then we have the ranking on the most important features based on this classifier. Another one is by using the Shapley values to obtain the most contributed features for the predictions of the model. And the third method, which is the LDA-based approach, which selects the most discriminant features. So for the task of gender classification, here we use the spine 15% sparsity. Here we trained a random forest classifier on VoxLab1, which gives an accuracy of 99%. And we selected the 6 most important features using the 3 selection methods. So just to say that using only those most important features, we get an accuracy of 75% for this task. And to explain this nice plot, here we have the most important features, and the line linking each feature to each method. It represents the importance of this feature selected by each of the methods. We can conclude from this that the three methods selected, the most selected, have the same. The three methods are commonly selecting the most important features, but then at the end we see that there are some difference of this selection with respect to the three methods. Here is the same thing, but with the spine 70% sparsity. So next. The next goal is to have a mapping between the representation word and informative word. So the representation word here represents our binary spine vectors, and the informative word, we choose it to be the OpenSmile descriptors, which is the set of EGMAP's 88 functionals of F0, formats, spectral, etc. And we choose 4 different selection methods to select the descriptors that describe best the most important features related to gender and emotion detection tasks. So one method is to calculate the correlation between the features and the descriptors. Another method is based on the importance of each descriptor using the Gini importance or Shapley values. Another one is based on the discriminant power of each descriptor, and the last selection method is an entropy-based approach, which combine many descriptors and give us the most important ones based on the interaction between all of those. So just to give you an overview about all the methods, because we didn't choose only one method to do this selection, because for each one we have some advantages and disadvantages. For example, for Gini importance and Shapley values, they consider each descriptor independent of all the others. But since we have some correlation between all the descriptors, maybe it's not so relevant to consider this method. But for example, for SLDA, it selects the most informative descriptor for the task in question, and for the last approach, it takes, as I said, the combination of variables, because it returns more information than considering only one descriptor independently of the others. So this is just to show you the when we calculate the percent correlation between the descriptors that we have and the representation word, which are the features, we can find that there are some groups of descriptors that are related to some features. And here, if we use the Shapley contributions, we can, if we take one example, we can provide some local explanation for just this waveform. So for the representation word, if we take the dimension number 318, which is equal to 0 for this waveform, we have this explanation of this feature specifically. So we have a probability of prediction for class 0, which is 91%. Yes, 91%. And we can see also the descriptors that contributed to obtaining this value. To have a global explanation for all the examples that you can have for gender classification. So here it's just for the system spine 15. This is the same plot that I presented. Here we can find for the most important features that we selected for the gender classification, we can find that there is some descriptors that can describe those features, which are mostly related to F0, which we know that it is a very important descriptor for gender classification. Another example here, but it's for emotion detection. So for emotion detection, we take also the most important features and we describe them. We find that there are some family of descriptors which are related to MFCC, loudness, voice quality, spectral, rhythm, and formats. So here, just an example of an explainable speaker diarization use case. So here it's a real example from ELI's data. We have the segmentations and we have the gender of each speaker. So from the representation word, we can extract the spine vectors. We can have, if we take the most important dimension that we selected as important for gender, we can provide the explanations for this dimension for each segment using Shapley toolkit, and for each segment we can provide the descriptors that contributed to that feature. So to conclude for all this part, the question for this part was how to get an explainable representation space by applying some constraints on it, and how to interpret this space. So we did this by constraining the representation space as Antonio presented with his methods based on the attribute, doing a speaker characterization. And we found that it reinforces explainability, and also using the spine vectors, we found that binarization is definitely useful to provide more explanations. We obtained some linkage between the representation word that is abstract and the informative word, which represents a very nice step towards interpretability. And also, from what Anna presented, we found that including confidence on the embeddings, which are the XI vectors, open a new perspective. And for future, we are maybe we can explore a larger informative world, including phonetic and linguistic information. So let me leave the space for the third part.
Okay, hello. I hope you're still there. We are reaching the end, so we almost got it. So on my side, I will let the speaker embeddings aside and talk about multi-label segmentation. And we have seen before that a part of our team has developed a multi-label segmentation model, which is working okay. But the problem is that this model is a black box, so we would like to develop a more explainable model based on this black box model. And the idea here is to use a thing presented before in that paper, which uses non-negative matrix factorization, NMF, to include it into a proxy model that will reproduce what the black box model does. So, to research question, first, can we apply this method to the multi-level segmentation and reach similar performance as the original model? And second question is, what explanation can we retrieve from that model? So here is our architecture. I will go a bit fast on it because we are short on time. But the idea is that here we have the original multi-level segmentation model. So from the audio, we go to the logit, so the segmentation here. Then we have our proxy model, which is trained in a teacher-student manner, composed of two functions, the psi function, which maps the wave-LM features to the H embedding here. And then we have just a linear layer theta, which maps the H embedding to the decision space. So why are we having H here? So this is to fit the NMF framework. H is a time activation embedding, so it represents the time. And W is a pre-learned dictionary of frequencies, so it represents the frequency domain. And by multiplying W by H, we can reconstruct a spectrogram. So we are in the spectrogram domain. How do we train everything? First, we have a knowledge distillation loss here, so to make the teacher model fit the original model distribution. Then we have an NMF loss here So to do so, we extract the spectrogram from the input and try to minimize the distance between the target spectrogram and the reconstructed one. And finally, we enforce sparsity over H to make it easier to interpret. So first, the results. We tested this model around Aragon Radio, Die-Hard3, and Ally Skin Test, and show that the performance of the teacher and the proxy/student model are the same, or a bit better sometimes. And performance is nice, but then we have to explain, because it's our goal here. So to explain, I will only focus on the last part of the model, from H to the decision. So H is the embedding obtained for a given X audio segment containing one class. The first step is to apply a temporal pooling to H, so we get a Z vector of k dimensions here. So this vector is then multiplied by the weights of the linear layer according to a given class. So by doing so, we obtain a R value here, which is a relevance score. So we know that what component is relevant to classify one class. So nice, we are able to identify which components are relevant for the classification. But then we have to use this. So keep in mind that by multiplying W by H, we are able to go back to the frequency domain. Then from the relevance vector, we are able to select some components given a threshold and get a new vector. And since they lie in the same space, we are able to project this relevance into the frequency domain. So we will get something like this, so a W matrix, some activated components, and we get something in the frequency domain. This is nice, but we have also to measure how removing components are impacting the decision of the model. So, from the selected components, we will just keep them in H and get the decision from the masked H version. We can do this kind of plot then. So on top you have the frequency versus the threshold, and you have the relevant component for the classification, and we are increasing the threshold, so we are reducing the number of activated components. And under you have what I have called confidence, but it isn't a real confidence, it is the model output. And so we see that by removing some components, we are decreasing the confidence of the model, which makes sense. And also, we can identify which components are really relevant to classification and what we should not remove. Then we can compare between speech, music, and overlap speech, and see that the frequency bands used by the model are not the same. But this is local, so we can do this at the segment level. What we want then is a more global explanation. So we will do this relevance vector extraction for a set of segments, for a set of classes, and get an average relevance vector over this set of segments. And we can plot this kind of thing. So we have, on a global point of view, the average relevance of each NMF component, and see that some are common between overlap and speech, for instance. Some are really discriminative between speech in blue and overlapping speech in orange. Also that some are really specific to music and some specific to speech. So by doing so, we know that from these components that we can project to this frequency space, we can identify what information in the data is used or necessary to classify each class. So to conclude on this task, on this part, we propose the proxy model, which is trained in a teacher-student approach, which tends to do multi-level segmentation. So we applied the NMF framework to make an embedding to spectrogram mapping and explain the decision of the model in the embedding in the frequency space. The results show that the performance are similar between the teacher and the student, and also that we are able to explain things. So yeah, we have things to improve that are listed here, and we can discuss later. So I'll give the floor to Thomas.
Thank you. So hi, I'm Thomas, and I'm wanting to look at what happened on diarization systems, especially the clustering-based one. So they're using X vectors, so I need to look on the spectrogram what makes two X vectors similar. For that, I used a visualization technique, so we're going to see some images here. That was initially made for images, but here we're going to try to look at where are the gradients on the spectrogram when we generate X vector. So we're taking two spectrograms from the same speaker, two different spectrograms, and we're gonna look at what makes them similar according to our loss. But because they're gradients, we want to integrate them to have something more visual. So as we fade our target spectrogram, we're going to integrate also little fading parameter alpha to get gradients. So these big image are the gradients for one spectrogram, where are the areas of interest in terms of temporal and spectral place. So let's take a look. What can we see? We can see that whenever there is no speech, like breathing parts, there is no gradient. It's not useful for authentication. And we don't have a uniform distribution of the gradients. Some areas, some frequencies are more used. So we're going to try to look with the information we have, one of them being the alignment with the phonemes. Where are some phonemes, and is the linguistic information linked to where we have more or less gradients? So we segmented that, and we looked at which phonemes have more information. And it seems that in blue here, vowels contain slightly more information, of course being normalized by the energy and the time that they were used. But still, vowels seems to contain a bit more information than various consonants. So we try to divide them by different phone categories using the manner or the place. It's not really significant, the variation. We still have each time our blue bar vowels that are still more used. So we try to look per speaker. This is measured on a Voxelab 1 set. That's why we only have 40 speakers here. And there is still some variation for each speaker on which is going to use more this or this category of phoneme. Overall, I'm going really fast here because we don't have a lot of time. We have a technique, integrated gradients, that is also really fast to use a compute, and it precisely enough can show you in different parts of the spectrum what is used. It's not going to be uniform across the phones, but we can at least see that vowels are going to be slightly more used. We have two perspectives on that. One of them is specifically the impact of some phones, not on the gradients, but on the performances, and that's what Gabriel can present just after. And the other one is how can we mix it with other explainability techniques, like how those gradients would behave in a constrained space, and that will be for another time. So I'm going to give the mic to Gabriel.
Hi, everybody. Beginning the war in Le Mans with this question. In reality, I don't sure if we have resolved in the beginning the war, but first we control one system based in two principal states. The first state, the idea of the first state is find the phoneme timeline for each signal in the speaker recognition. And the second state have several categories of phoneme based on Montreal force alignment. First, you want to select one category for one vector, you can use, or you can mix to several categories. You can use the vowel, you can use the nasal, the consonant, and you can use all the content, the voice content. And for this, we have the first result using the consonant and vowel. The consonant is all phoneme different of the vowel. We have 40 equal array and 6 equal array, but you see the time used for each category. You know that the vowel use less information, less time in the signal. Then we prepare one method for fix the time for two signals using the random method, of course. And you can see similar equal array when using only the 37% is the time for each signal. What happens is if use the consonant and vowel for speaker recognition, using only the 37 second, we have 3.9 for equal array. If you compare with the baseline is X vector based on speech brain, we have 5 of equal rate. Is good using all the phoneme in the signal? Is good use all the voice content or not? Then the next experiment, we prepare
one baseline using all the signal. We have 0.8 of equal rate. You use the consonant and the vowel. When you use the consonant and the vowel, you use all the voice content in the signal. We have 0.9. It's very close. It's good for us. But when you see the average time used for all phoneme, you can see 83% of the time. Then when you fix the same time for the baseline, we have very close result. It's good result for us because show us we have used all the voice content in the signal. We use the good information from the speaker verification. Then we see what is the next experiment. What happened is I use the common font between each part of the signal for speaker verification. Well, we have 2.3 equal rate using the common font. But when you see the time, you find you use only 45% of the time between each signal in the speaker recognition. What happened is use the same time for all the phoneme in the signal or for the baseline. Then using the common font, we have the better result. It's very instant result. I think we can continue work on this, but for me, this good result. But the principal result in the world is not for speaker recognition. The principal result is for control the word space, control what are you using for obtain the embedding of the speaker, because you can now use several signals of the same speaker for control 2 embedding, 3 embedding, 4 embedding. Then you have what is the difference between these 2 embedding. The speaker is the same, the content is the same. Maybe you can find the similarity between them. Similarity refers the dimension of the embedding. Or you can change for different speakers. You can use several signals for each different speaker, and you can find the difference between the dimension of each speaker. Or you can find the gender different of the speaker. Is the final result.
Hello, I'm Norbert, and the problem here is how to organize some space to compress the descriptor coming from the real world, which could be X vector in the high dimension and irregular one, to the conditional latent space where this will be regular and in low dimension. And from then, you can, from this latent space, you can see how to obtain the pseudo label and compare this pseudo label from the label coming from the input or from the acoustic description. To do this, I will skip. To do this, we introduced some constraints during the training of the variational autoencoder. This constraint was just a label of the data, and this forced the latent space to be organized into many clusters, where each cluster is just one class. And then we can go from this cluster to obtain the pseudo label, which are also the label in the data, and we compare them. This was just inspired by this article, and we train, but we are not trained like them, but we train using the centroid reconstruction as our prototype. To the evaluation, we calculate the score, the label matching score between the pseudo label and the label coming from the real world, and we also evaluate the link between this
the latent space dimension and the dimension coming from informative world. This was done using linear regression. And then for the first evaluation, we trained the model using 2 dimensions in the latent space, and for the classification problem, which was 2 class, we also used 2 prototypes. And the matching score was more than 99%. And from then, we used the decision tree, which is for us a white box to see which part of the descriptor were responsible for the classification. After this, we trained also linear regression and to see also which part of this descriptor was responsible of very linked to the each latent space dimension. And from then, we saw that they renounce the same features, but the feature obtained from the anti-set of feature was just a derivative of some features in the provided by the decision tree. We make it for all the dimension, and then we can conclude by this word the latent space. The concept we introduce in the latent space permits to well organize this latent space, and then the latent space, as it is in the few dimension, we can visualize and analyze easily. And for the next, we will try to more calibrate the parameter of the model, and we also test it on some other classification problems. For the takeaways of this group, in this group, the main question was which part of an audio signal are the most important for some speech processing tasks. For the audio segmentation, the group proposed the non-negative matrix factorization to see which part of frequent band is responsible of different segment of after segmentation. For the speaker verification, the group proposed to go back to the spectrogram and see which pixel in the spectrogram is responsible, characterize each speaker, or which phoneme can be changed to go from one speaker to another. And from the last one, we combine acoustic features and X vector for the gender classification. I will give the floor to Marie for the final word.
Thank you. I am really pressed to conclude because I have at least minus 15 minutes to do it, so I'm going to be very fast. So for the evaluation, I will skip this part, but we have 2 ideas. We can discuss it after. So our goal was to provide a multitask, multimodal speaker diarization input and provide some list of attributes. So we have done this work. We have a framework to use partially annotated data and calibration. We have demonstrated that the linguistic information can be useful for the diarization in complementation to the acoustic diarization. We had a second goal that was to explain the decision of the model. So it's still pending because it's a very good, very huge work that requires a large amount of people to do it. So we have shown that the binarization is definitely useful and that we can constrain the latent space in order to have better explainable model. And we have also enforced the linkage between this representation and this informative world in order to have this more theoretical formulation of the problem. So maybe we are here. We were at the starting point. We were looking for good performance, and then we come at the workshop JSALT. We have explainable representation, and so far we have reached this point towards informative world. Maybe in another step, I don't know, maybe 2030, we will be on the top of the mountain. So I just would like to thank the Esperanto project, also Jean-Zé for the computational resource. Thank organizers and colleagues for support for this big workshop and big work. And this is the list of the participants, so that's why we're late, because we're not a huge number. And I think we are at the end. Thank you. They just want to eat.
So maybe they can ask about the menu. I don't know. So I have one. You've been working on diarization. So diarization is nice because there's segmentation. So there's temporal activity. There's speaker identity. So actually, it covers a lot of tasks in speech. How do you perceive? How do you see the future for this? How to transpose this to other tasks in speech? ASR, translation, whatever.
I think there is a nice panel of people that can answer also this question. So here in this workshop, we tried to make some general formulation of the problem. So we can adapt it. We have tackled the problem of diarization, but of course we can apply this formulation to other problems. In details, I cannot answer, but if there are some people that have more.
Thanks. Is Anna here? Okay. Sorry, you moved. I have a question about the SNR as the feature for the branch for the uncertainty neural network.
Mm-hmm.
Like, how do you know that it's better for the uncertainty and not for like adding the SNR? Like, have you compared the experiment if you add the SNR as an input feature?
To the
generally to the original network, yeah.
No, I didn't do this experiment. We can try, but I don't know. So here the motivation is that if you have higher noise, you should have lower precision. So it was used only at the input of this particular branch, which extracts the precision. So the rest of the embedding extractor didn't see it.
Yeah, like my question is whether it was like camouflaging the uncertainty as SNR predictor, for example.
I don't think so.
Okay. Yeah. And maybe a little bit like a related question is, can you train the model in like multitask learning, not to have it as a input, but the like base model to like be able to give you the representation which has the SNR information there? So you don't have, like, you have single model and you don't have to plug in the SNR at inference.
I'm not sure I totally understand what you mean.
So I was, maybe I can recapitulate. If you have like the basic neural network model doing two tasks, like, and the new task will be the SNR prediction, it should have like, you maybe have, you can use it directly for the SNR, for the uncertainty estimates. Like, do you think like the multitask learning with like additional task of SNR is something?
The way I see it, maybe not additional task of predicting SNR itself, but you can add additional loss to these precision matrices that you estimate and try to encourage them. Again, at training time, you would know which utterances are noisy, which are not. So you can try to push the precisions for the noisy ones to be low and for the clean ones to be high. So kind of in this way, I think you can approach it. But there is no motivation, at least in this framework, to estimate the SNR itself.
Okay, yeah, thanks.
There is some comment.
I just wanted to complete by the fact that the
precision is not a measure of the SNR. SNR is just a marker of low precision. But precision here is really more than that. It's how much interesting information or how relevant is the embedding in terms of task-oriented information. And the task-oriented information is not detect the SNR, it's detect the speaker. So it should be more relevant to the amount of speaker information present in the embedding and the relevance of this information that SNR. Of course, if the SNR is very low, there is few information, and it's what Anna measures in this case.
Mm-hmm. Yeah, thanks.
I guess it's nice summarization of this.
Any other question? Maybe online? Please try not to give the answer in your question.
I'll see the comment.
Yeah, it's for Thomas. Sorry, Thomas, but you said at one time that integrated, it's linked to the previous comment, in fact. Integrated gradient is indicating the amount of speaker information present at one place of the file. Are you sure about that? I'm not sure about that.
No, that was to gain some time to simplify the explanation. It's the amount of information that's going to be used for the system to distinguish or to get two iterances from the same speaker closer. So because I'm using a really small data set, I cannot say if it's exactly the speaker information, if it's any other bias from the system that's used, but it's allowing me to look at where are the areas on the spectrogram that are used by the system to determine that two segments are closer and closer in the latent space of X vector.
So I have a complementary question. If there is a gender difference between two speakers, so something very easy to find, do you think that the integrated gradient will show a huge activity or only a small activity but relevant to gender information is enough to make the difference between the two speakers?
That's a good question. I don't think we're gonna have a more or less information because I'm normalizing the gradient I'm showing you. But maybe the localization is going to be different over different band of frequencies than different difference between speakers. If it's just gender difference, maybe it's going to be on a smaller area.